Alright, hello everyone. Welcome back to our regular class meetings. How is everyone doing today? Hello Amanda, hello Dylan, hello Rachel, hello Tristan. Okay, morning. Checking video and audio. Is everything good on your end? Alright, then we are ready to start. So make sure that everything here is okay. Alright. So just in case you didn't notice, your grades are already updated. That means Alex grade, Esposo grade, tests, all quizzes, everything is up to date. So if you haven't checked those, you might want to check what is your grade right now. Maybe do I have another thing to say? Okay, there was an issue with knowledge check number 2. I'm still working with that. A few of you lost working out from the knowledge check and lost your progress. A few of you have been able to redone everything again. Okay, and that's pretty unfortunate. I apologize for that. That's an issue with the system. But I'm still looking for answers. So when I have those answers, I will communicate them with you. All right. Okay. Any questions? Okay. Yesterday I uploaded a document with laws of exponents. These laws are particularly important for us because now we are going to start working with two type of function, or maybe we are going to treat those functions, but they are more behind the name or the adjective of a function. Now you are going to see, and before going through this, I should put this. Can I have the page? Thank you. All right. So far, we say that they are 4 basic mathematical operations. And those are addition, subtraction, multiplication, and division. We treat these 4 as operators in math. But there are also functions. The function of addition, the function of subtraction, the function of multiplication, and the function of division, right? So we have been working with functions all this time along. And since these are very important functions that we use daily, then we give them like a proper name, like math operators, addition, subtraction, multiplication, and division. So all this time you have been working with functions, right? Now, what we are going to do in this next topics or units is that we are going to learn 2 more functions that we are going to treat them as mathematical operations. We are going to talk about exponential functions or exponents. Okay, so we are going to treat the exponent now as operator, and we are going to work with the logarithmic functions. Logarithms are related to the exponential functions. Okay, these two are related. Okay, and you will see we are going to explore their definition as a function, but then we are going to use them as math operators, which is the same at the end, but it's just to put things in perspective. All right? These four are the basic mathematical operators. Okay, but they are function as well. You will see the following. Remember that we learned about the function and its inverse. Well, addition and subtraction, they are inverse to each other. So if we take addition as the original function, then its inverse is subtraction. The same with multiplication and division. The same with multiplication and division, they are inverse to each other, and the exponential function and the logarithmic function also they are inverse to each other. This is the reason why we are able to solve equations. So when we are going to solve the following equation, for example, let me put it below, or maybe okay, so why can we solve equations? Let's suppose that we have the following. We want to solve for x. What we do? First, we do the order operation but backward. So in this case, we have multiplication and addition. So those are the two mathematical operators that we have here in this equation. We want to solve for x. So backward on the order, from the order operations, we do now addition first, right? We treat or we work with addition first. The inverse operation, the inverse function of addition is subtraction. So that is why we are able to use, or that's one of the reasons why we use subtraction to cancel +4 from the left side of the equation and bring -4 to the right side of the equation. Remember when we combine the function and its inverse in a composition, it gives us back the input. See? So when we did this, we got back the input. Okay, not the output, the input, because these two cancel each other in the composition. So that's exactly what we are doing here. We are canceling addition and subtraction. Okay, so that's why then we got the following here down below, and we do the same again. What is the inverse operation or function of the function of multiplication? It is division. So we divide both sides by 3. So we cancel multiplication with division, and then we have found the value for x that solved that equation. Okay, so we know how to work with equation. Primarily, we have been working with linear equations. Then we have learned about quadratic equation. This is going back to the polynomial. The higher the degree, the more difficult is to solve that equation. But we have learned general techniques to solve any kind of polynomial. At least polynomial with rational zeros and complex zeros. All right? So this is important. I want you to take this, to have this in your mind, because we are going to do this exact thing that I just presented here. What we have been doing before is solving the equation with addition, subtraction, multiplication, and division. Okay, so we are going to continue solving equations. Also, we are going to explore the properties of exponential and function, logarithmic function. Okay, but the practical uh, applications that you want to take from these units is that now you will be able to solve all the kind of equation that contain exponential function or the exponential operator and logarithmic functions, or the logarithm or logarithm operator, right? So you will see the relation of this topic with solving an equation with the example that I put here on the right side just in a moment. You will see some kind of equations. If you have look at the work the other day at the last three exercises, are equation with an exponential operator that you need to solve, right? Okay, so yeah, we have covered the math operator and we have covered the two new function or mathematical operator that we are going to learn from this topic. So because now we are going to be working with exponential function. Exponential function is where the input is on the exponent. You want to know first the laws of exponent, and you want to know how to apply them, okay, in mathematical expression. Because again, we are going to be working with the equation. We are going to be solving equations that contain exponential operators there. Okay, when I say operational operator, is that now the exponent will contain a variable. Okay, so what you want to do here, see that we are working here in general because we are working with variables. So you want to know how to apply the laws of exponent. So this exercise is to practice the laws of exponent and how you can use this will help you to then manipulate the mathematical operations that have exponents or exponential operators. Okay, remember, you want to simplify, you want to find ways to solve the equations. Okay, so this part is important. You need to be able to use these laws. Okay, so for example, the first one, we have x raised to the power of n. That means that we are going to multiply x n times. Okay, the example is if we have 2 raised to the power of 3, it means 2, we multiply 2 3 times. Okay, and this is too bold. Okay, help me on the second one. What will be the result here? Okay, Amanda, I have here that you are adding n and m. Okay, anyone else? In this, when we have this kind of expression, we multiply together the two exponents. Okay, so how I look this or how I read this? Well, we have x raised to the power of m. Okay, and then this whole expression within the parentheses is raised to the power of n. So it will be the same as x to the power of m times n. Okay, and it could be n times m, it doesn't matter. It is multiplication. Okay, an example, this is the same as 3 times 4, which is 12. All right, 2 to the raise of 12. And this one, Amanda, yes, this, when we have this is when we want to add the exponents. So here it will be n plus m, right? So we have a multiplication of two exponential expression here, x to the n, x to the m, because the base of the exponential operation is the same, x. So we combined this multiplication as and just x raised to the power of the sum of the two exponents. Okay. So in 3 we were multiplying. Now we are dividing. So what will be the result here? And here now we are going to subtract the exponent. The base is the same. We have a division or a fraction. The base is the same, so we can subtract the exponent. Careful, because now we are going to be working with subtraction. So that means that one of these exponents is going to be negative. The order will be the exponent from the numerator minus the exponent for the denominator. Okay, this way we make sure that the exponent on the denominator is the one that is negative. So let me give you an example here. Okay, so this when we multiply 2 raised to the power of 3 times 2 to the power of 2, it will be the sum of 3 and 2, so 2 to the power of 5. Okay, so 2 to the power of 2 divided by 2 to the power of 5, we subtract, taking into consideration that now 5 is going to be the negative value, or is going to be, we are going to subtract 5 from 2, so that brings 2 minus 5, or that is 2 minus 5, so 2 raised to the power of negative 3. All right? What about number 5? How would you write the right side of this number 5? In number 5, when you have an exponent, or I think I don't know, an exponent that it is covering the parentheses, right? Or an exponent that applies to what is on the parentheses, inside the parentheses. If we have factors in the parentheses, then it is like distributing the exponent with all the factors. X to the power of n times y to the power of n. Okay. This one we use it mostly when we have variable inside the parentheses that we cannot multiply together. Because if we have, for example, two numbers that we know that we can multiply first, we multiply these two first, and we got 6 raised to the power of 5. But this is the same as 2 to the power of 5 times 3 to the power of 5. Okay, but doing this is making it more complicated. So I will go first and multiply the two factors inside the parentheses and then apply the exponent. Yeah. I was able to multiply the two factor because I have 2 and 3, and I know that what that multiplication is. But for cases where we have a variable, then if we're only want to distribute that exponent. Okay, so see the difference here? Okay. So this one, number 6, is almost the same as this number 5. Now that we are dividing, or we have a fraction, so it will be x to the power of n, y to the power of n. Okay, so it's like a distribution. Again, we do this if we cannot like divide or we cannot simplify the fraction. If the fraction contains numbers that we are able to do the division, so 3 divided by 2, so we will do 6 divided by 2, we will do that division first. For example, 6 divided by 2 raised to the power of 10. I will do first 6 divided by 2 and then apply the exponent. Okay, but in case that we do not know any, or we have variables like here, then you want to distribute the exponent. Number 7, a very common mistake I have seen from my past student is that they put this. Okay, and this negative in the exponent doesn't makes the entire expression negative. Okay, and this one is important, and we are going to get back to this one when we start working with exponential function. But this negative here, the negative on the exponent, what is give off is the reciprocal of the expression now with the exponent being positive. All right, so this negative here brings this expression to its reciprocal. So if the expression is in the numerator, then it goes to the denominator. If we have the following, like 1 over y to raised to the power of negative m, then we have y on the numerator with m being positive, the exponent being positive. Okay. Well, that's number 8, and we can see it here. So number 8 is 1 over x to the negative n, so it will be x to the power of n. This one is also important, another one that we are going to use. What will be this value? Anyone interested in why this is equal to 1? Anyone? Why? This seems weird, right? If I raise something to the power of 0, I got 1. What is that? Any idea? Okay. What you think about this, I will do the number 10. Number 10 is basically we are going to combine number 6 and 7 and 8. Okay. So in number 10, I got negative n, so I distribute the exponent of negative n. Okay, this is one way to do it. There are other ways to do it. So this is one way to do it. Another way to do it is that we do the reciprocal first. So now n is positive. Okay. and then this from the first option here, or from the first, let me put here, the first application of the law, or my first interpretation here, we have these two n that are negative, so we put below or in the denominator x raised to the power of n, and then y to the power of n. Okay, you will see if you distribute now in this occasion the exponent with y and x, we are going to get the same results. All right, and here we have negative exponents, so we go and we put n in x to the power of n in the denominator, y to the power of m in the numerator. Okay, all these laws will allow you to manipulate the expressions later to solve the equations. Okay, let me go back to number 9. Okay, so I found this one interesting because for me it's kind of weird. Any number 1 million raised to the power of 0 is 1. So let's explore just this one out of curiosity. I promise it's going to be quick. Okay, so we know, can you help me with this? 2 divided by 2, what is that value? It is 1, right? So it means if I take a variable, yeah, a variable, and I divide that variable by itself, we don't know its value, but what would be the division here? Because we are dividing the variable by itself. It is going to be 1 as well. So we know if we divide a value by itself, its result is going to be the same. So if we divide 3 raised to the power of 2 by 3 raised to the power of 2, it's going to be as well 1. Okay. Well, what happens if I divide x squared by x squared? We should get 1 because we have the same expression on the denominator and numerator. All right. So are we agree with this? Is this okay? Okay. So let's continue with this one. But now let's apply, before getting to number 1, to the value of 1, let's apply the laws of exponent that we have learned. So we have the same base, x. And we have a fraction, and we have 2 exponents. So let's apply that, the law that applies here. So we subtract both exponents. So because now we have x raised to the power of 2 minus 2, 2 minus 2 is just 0. So we got to this expression, okay? And you might be thinking, well, what is the value of this? But we know from the beginning that this is equal to 1 because we are dividing a value by itself. So at the end, we combine these two results and we put that as a property of the exponent, or a law for the exponent. So anything raised to the power of 0 is equal to 1. Okay? So I think this is interesting because yeah, this expression is kind of weird, and there is no way you can get its value unless you go through it's not a hard proof, but at least it gives us some kind of perspective. Okay, so this is a good opportunity to show you a little bit of math when we talk about math as pure math. Okay, in a college algebra class. Okay, so any value raised to the power of 0 is going to be 1 because it means that we are dividing that value by itself. Okay. So you will see how all this is going to help you in our units. Okay. Sorry. All right. So another thing that we're going to go over before we start with the exercise is what is an exponential function. Okay, so here basically what we are going to do is to explore the parent function of the exponential function. Okay, and we are going to go through its properties. Okay, like we did on unit number 2, I believe, or until 3. Okay, we are going through its properties, and also we are going to explore the transformations on the exponential function. So we are like going back, we are closing the loop or the circle. I don't know how you say that in English, but we are going back to what we learned from test number 1. But now we are going to apply to a new kind of function. All right. So in the book, you have this expression for the parent function. All right. And you might find this interesting that we are not using like a particular number. We are using C as a variable, capital letter C, and A as the base. The first thing that you want to make sure, or I want to point out, is that the exponent here applies only to A. The writing of this sometimes it might confuse you. So sometimes I use parentheses to make explicit that the exponent x applies only to A, and then C is just a factor. Okay. Okay, so C could be any number. So a real number. Okay, and it's just going to be just a factor that we multiplied by the exponential expression. The exponential expression will be A raised to the power of x. Okay, so you will relate C to the vertical stretch or compression. Okay, so the transformation of the vertical stretch or compression. You will see how that how we use C in our exercise. Okay, but remember that that C is a factor that is being multiplied in the output group of the function. Okay, so that value will stretch vertically or compress vertically the graph of the exponential function. Okay, so now this is the part that is the core of this function, where we have the exponential. I think I should put this here. The exponential expression here, right? So we have A, we call it the base. And what makes this an exponential function is that the input is on the exponent, okay? We haven't seen any function where the input is in the exponent, okay? So that makes this expression as exponential expression. Okay, A has a few conditions. The value of A need to be positive and it can be equal to 1. If A is negative, then we don't have a function. And let's explore why A can be negative. Can be negative. Okay, why A can be negative? Okay, so let me bring Desmos here. By the way, let me show you a few projects for my past classes. Okay, this is not related to the class. This is just if a few of you are like interested graphing, how do you say, art, but virtually, so graphing art, I believe is the term. If you're interested in that, I can help you with that. I am first a math teacher, but also I am a programmer, more specifically a video game programmer, and I use math and programming to create animations or anything that need to be created, right? So this is an example how we can use what we are learning, the coordinate plane. This is just the graphing calculator from Desmos, and taking a few pictures and manipulating them. I don't know if you have noticed, but this is Columbus. You can create some kind of animation. Yeah, my creations are very silly because I'm not a good artist. But you can see that we can use math to create some kind of art. These are projects from my past students, okay, from other classes. Okay, so see that we have here some kind of animation using functions and transformations and just pictures. So it is important for me to show you this because you are learning math and sometimes you don't know where you are going to use math. Well, if you like art, you can use math to create art. Okay, sometimes it's kind of weird. Well, math and art, they are not like taught like they are connected, but yes, they are connected. So let me see if I can show you one more thing, maybe a silly thing, or maybe something that okay. And this one is a more elaborated animation, and this is using trigonometric functions. So see that with math we can create like those kind of weird but cool animations. Okay, I think I have one more that is cool because the other one are very silly. Yeah, see, you can explore and make those kind of effects that look cool on the coordinate plane. All right, but that's just extra stuff. We want to know why exponential functions, the base cannot be negative. All right. Okay, so what you are seeing right now is, I hope you can see this well, but here is the exponential function, the random function, where the c value is just 1. So I'm selecting c equal to 1, so the factor that is in front of the base. Okay, and you can see here that we have when a is positive, greater than 1, we have this shape. Okay, it's a shape like it's going exponential up. Okay, when a is, and in this slider I changing the value of a, so a right now is 4.1, and you can see that I can bring it down. When a is less than 1, you will see that now the graph goes, or the behavior of the graph is a decreasing behavior. Greater than 1, increasing. Below less than 1 is decreasing. But see what happened when I make a less than 0, so negative. The graph disappeared. Okay. Now I am presenting some points on the graph. Okay. Okay, so you are seeing an orange, a green point, and red, purple, and blue points. You're seeing that, and you're seeing another point that is a tiny point that I can move around the curve of the graph, or the graph. Okay. I want you to focus on the purple one, the purple one, the one that it is here, and I want you to see what happened with that point when I mix a negative. Okay, so see all those points, because our point on the graph, they still in the graph. Okay, and so this one is not good because, okay, but now we are seeing a there. So a is there. A is, the purple point is still there. A is positive, is 0.2. Let's make a negative. So now, where is the purple point? Why can't we see it? What's happening there? Now that a is negative. So see that we can see the other points, but a, or the purple point, is not here. If I bring back a to be positive, we are seeing that purple point there. Okay, but negative, then there's no purple point. Okay, so this is one of the reasons why the base of the exponential function needs to be positive, because now we are missing information when a is negative. And it's not we are missing information, is that now we know that the coordinate plane right now is based on two number lines that represent the real numbers. When a becomes negative, then we are getting complex numbers, imaginary numbers. So we are not seeing those here in the coordinate plane. That is why a needs to be positive in order to have an exponential function. Otherwise, we will have all the things. Okay. So that is how we explore this using just the graphic calculator. But I don't want to save this. But we can go further and explore what happened when a is negative. Let's suppose that a is equal to -2. Okay. And let's say that we are going to calculate with negative. So the function that we are going to use is a raised to the power of x. Okay. C is here, is the value of c is just 1. So f of -3, f of -3 over 2. Okay. And we can continue -1, 0, and so on. This is the input, right? So the input could be a negative number because we are working on a function with a domain on the real numbers. So a is -2. So we have -2 raised to the power of x. So -2 raised to the power of -3. We use the law of exponent to get this value. So it would be 1 over -2 raised to the power of 3. That is 1 over -8. So -1/8. Okay, so this is a real number, so this is okay. What happens when we use -3 half in our function. So we have 2 raised to the power of negative 3 half. So we know by applying the law of exponent, we use 1 over negative 2 raised to the power of 3 half. There's a relation between the exponential expression and the radicals. I don't know if you have learned from the previous classes, but when we have the following. Okay, so this is a radical here. For example, square root of 4. Square root of 4, this part here is where we put the index. So here is, if the index is not there, it means that the value of the index is 2. Okay, but we can use other indexes, cube root, or cube root, I don't know other vocabulary about radicals, but if the value of the index is 3, then we say cube root, right? So cube root of 4. The thing is that we can change this expression to a radical expression to an exponential expression, where we take the exponent of the radicand is what is inside, and we divide it by the index of the radical. So n divided by n. Okay, these two expressions are equivalent. Okay, so this is the same as 4 raised to the power of 1/3. Okay, so we are going to apply this same expression here, and let's see what happens. So it would be 1 square root, okay, 2 goes here, of negative 2 raised to the power of 3. This is equal to 1 over square root, so I'm not going to put the 2 here as the index. And we know that negative 2 raised to the power of 3 is negative 8. What we learned from the past units? What is the meaning of that negative inside of a square root? When we have a negative in the square root, if you go to your calculator and try to calculate the square root of negative 8, what value are you getting? Okay, if you go to your calculator and put square root of negative 8, are you getting a value? Are you getting something that is undefined? Let me know that on the chat. It is undefined, right, Amanda? The calculator right now, it is set to real numbers, okay? To real numbers. That's why it given us undefined. We know from the past unit, because we learned about complex zeros or imaginary numbers, that is the same as square root of I. But when we have I, we are working with imaginary numbers, not the real zeros. So there's no way we can see this value in a coordinate plane where the only numbers we are representing there are real numbers. That is the value. That is the reason why the purple point that I just presented to you a few minutes ago disappeared when the value of A becomes negative. Okay, let me do something here because I see. Okay, I think my webcam is not working good. All right. So this gives you a reason why A can't be negative. Okay. don't get me wrong, this is not something that you need to know for the exercise of this class. This is not something that you need to know from top to bottom, because you will see that the exercises on this class are more practical. Okay, the only thing that you need to know that a need to be positive and cannot be equal to 1. Okay, cannot be equal to 1 is because 1 raised to the power of 2, 1 to raised to the power of 3 is always 1. So it just gives off a straight line. Okay, a constant function of 1. Okay, that's why a cannot be 1. Okay, but this part here gives you some insight of why the base has those conditions. Okay, and again, this is not something that I want you to know exactly top to bottom. This is just now when you're working with exponential function, you know why a can be negative, right? But you are not going to ask to prove why a cannot be why a can't be negative in the test or the exercises. Okay, this is just extra content that will help you to understand math beyond our class, and it will help you on the future when you are working with more advanced classes. Okay. So that is the exponential function. We know c could be any real numbers. The effect of c will be a vertical stretch or compression. Okay. The input of the function is on the exponent, and that makes this an exponential function, and the base has a condition. It needs to be greater than 0, so positive, and cannot be equal to 1. Okay. We have two type of behavior for the exponential function based on the base, based on the value of the base. So the behavior okay, behavior. So we have the increasing behavior, increasing and decreasing. Okay, I need to double check that spell. Increasing. Okay, increasing. Okay. Decreasing. All right. Decreasing. Increasing. Okay. So we have increasing behavior, and this is the shape of the graph. And we have a decreasing behavior, and this is the shape of the graph. Okay, increasing behavior is when the value of a is greater of 1, and decreasing behavior is when the value of a, the base of the exponential function, is between 0 and 1. All right. We have another thing, that we have a horizontal asymptote. The horizontal asymptote of the parent function is y equal to 0. Okay, so there is a horizontal asymptote at exactly the x-axis. Why is that? It's because there is no way we can get a negative value. Okay, there's no way we can get a negative value from the parent function. This expression here will never give us a negative value unless c is negative. But if c is positive, there's no way this expression could be negative by any way or any mean. Because when the input is negative, the exponent is negative, and we have seen from the law of exponent that a negative on the exponent, the only thing that is that flip the mathematical expression. So anything on the denominator, we go to the numerator and vice versa. But it doesn't make the value negative, all right? So the horizontal asymptote will be y equal to 0. If there is a shift, a vertical shift, so addition to the output or subtraction, then the horizontal asymptote will move along with that movement, okay? But the parent function has a horizontal asymptote at y equal to 0, okay? All right, so I've been talking here for an hour about the exponential function. So I don't want to continue boring you, and let's move to our exercises. So let's take a break, 5-minute break, so you can collect your thoughts, you can walk, stretch. Then we are going to get back here in 5 minutes, maybe more, if you need more, to do our exercises. You will see that I have spoken too much, and we have only 4 exercises. All that thing that I've just said is going to be applied here very quickly. So this is a unit that it is fairly easy if we compare that with test 2 material. Unit number 10 is going to be very straightforward. Okay, the most important thing is that you know how to handle exponential functions. Okay. Now I remembered I forgot something, but this is very easy and you will see. Before we go to the break, there is the initial value. The initial value of the exponential function is when x is equal to 0. And we call that initial value because x, like x is equal to 0. If we see it on an exponential function, c, the value of c here is 1. Okay, we are not taking into consideration the value of c. So we have the base raised to the power of 0, and we know by the law of exponent that anything raised to the power of 0 is just 1. So the initial value will be when x is equal to 0. The input of the exponential function is equal to 0. And this one is important, and you will see why. Okay, so that's enough for an introduction. Let's take a break, like I said. I will get back here in 5 minutes. If you have questions, prepare your questions, so when I get back, we can answer those, okay? I will see you in a moment.